Up until this point, we've talked about work and we've talked about power. Work is a force times distance. We have to remember that the force and the distance have to be in the same direction, so at times we have to use trig to find F in the x direction. Power is pretty simple. It's simply the work then divided by the time. The more time it takes, the less power. The less time, the more power. Now the question I have is, when you do work to something, it's a transfer of energy. We're doing the energy unit. Where does the energy go? If you learned in chemistry, energy is never created or destroyed. It simply goes to something else. So when you do work, now the next question is, what has it become? Let's take a look at this ride, for instance. For anybody who's ever been on the giant drop, the idea is that you're lifting up a bunch of people to the top. And so when we lift them up, think back to the Muscle Up lab. When you lift things, if it's at a constant velocity when you're lifting it, we can assume that it's the weight that's being lifted. So if we had this object that's being lifted, we're lifting it up with this force of the weight. And we know W equals mg. So the force is the weight. Now, another thing to consider is typically when things are being lifted up, we don't necessarily call it the distance, we call it the height. And so we've got a distance that's our height, and we've got a force that's mass times gravity because it's the weight. And so we're given something that looks like this, mgh. That actually stands for something significant. When we do work on an object to lift it up and we change its position, we have given it something called gravitational potential energy. It's the mass times gravity, that's that weight times the height. It gives us gravitational potential energy. And it's a form of energy, so its units are in joules. And so if I have an object and it has a mass of 100 kilograms, and I lift it 10 meters, I can multiply the 100 kilograms times 9.8 meters per second squared times the height of 10 meters, and I can calculate the joules of energy that it now has. Now it has energy, so it's sitting there up at the top. And when we look at things that are sitting up on a shelf, we don't look at it and go, oh look, it's got gravitational potential energy. Again, we don't see the energy in something, we see the transfer. So where does the gravitational potential energy go? What does that end up turning into? It turns into people falling. The giant drop, the thrill of it is once it's been sitting up there and it's gained its gravitational potential energy because the machine does work to give it potential energy, it then falls. And so that potential energy turns into something else. It turns into kinetic energy. And kinetic energy has its own equation as well. So today we're adding a couple equations to our toolbox. We've got GPE equals mgh, and now kinetic energy, it's the energy of motion. If something's moving and has a velocity, it has kinetic energy. It's 1/2 times m times v squared. Now there's something that's important about this, that's the velocity is squared. The fact that it's squared, so if your velocity goes from 2 to 4, the kinetic energy doesn't double, it quadruples. And it's important to understand that that square makes the energy really increase when you increase the velocity. So looking at this problem, it's important to note that we went from having potential energy up at the top, specifically gravitational potential energy, and as it loses all of its height, all of that potential energy is turning into kinetic. And so at the ground it has no height, but it all has kinetic energy. So all the energy at the top and all the energy at the bottom, it's still the same amount. It's changing from potential energy into kinetic energy. In fact, right in the middle, could you guess what it has? Well, it has both potential and kinetic. It has both. And so what we're going to be looking at in these problems is how the energy changes from one to the other in making some calculations to determine the velocity or the height at various locations. So that brings us to this idea that energy is always conserved. So the energy at the top of the ride is always going to equal the energy at the bottom of the ride. It's the total energy equals the total energy, and that's what you're seeing right here. Now when we put equations to it, it's actually this idea that the potential energy at the top and the kinetic energy at the top equals the potential energy at the bottom plus the kinetic energy at the bottom. So let's take a look at the example on the left and put the problem together. At the top, I simply label out potential and kinetic. Now you'll notice I'm just putting PE. Truth is, in this unit, we're only going to be looking at gravitational potential energy. Therefore, oftentimes, we'll simply just refer to it as the potential energy. Nonetheless, at the top, it's important to note that if the object starts from rest, there's no velocity. So there's no kinetic energy. Now, for this problem, that's what it's going to be. That's not always the case. If you're going to go on a sled, you usually get a kickstart. Or if you're on top of a roller coaster, you're moving just a little bit. But for a simple problem now, we're going to take a look and say, this thing's starting at rest. There's no kinetic at the top. It's only potential. Now take a look at the bottom. When you get to the very bottom and you're on the ground, you no longer have any height. And if you have no height, you don't have any potential. You simply have kinetic. Now what's important to note here is that the total energy at the top and the total energy at the bottom, according to the conservation of energy, must be the same. So these must be equal. So let's figure something out. Let's go ahead and say that the height of this is 10 meters. And let's say that the mass of this object is 5 kilograms. With that being said, I want to know what's the velocity at the bottom. First, I set up the conservation of energy. I say the potential energy plus the kinetic at one point equals the potential plus the kinetic at another point. Now in this particular problem I said let's solve for velocity at the bottom. So I'm looking for the velocity. I gave you the mass, we know what gravity is, and we have a height for our hill. So we can do some algebra and we can solve for the velocity of the cart at the bottom. I rearrange my equation so that I solve specifically for v. That does mean I'm taking a square root. I plug in my numbers, and then I put them in the calculator, and I get a velocity of 4.47 meters per second for this object at the bottom of the hill. Now, the significance of this problem, really there's a lot of applications. We could calculate what's the height of something if we know the velocity at the bottom. We can calculate the velocity at the bottom based on how high we put something. And we'll talk more in class about the various applications and more example problems.